If you see drag on the FE exam, you should be celebrating because these are quick questions that you're going to be able to knock out without a lot of brain power or stress. 2 quick questions in this short video because FE exam questions are quick. If you don't already know the answer, the way you start is by typing the keyword into your search engine, in this case, drag. And in the fluid mechanics section, you're going to get 3 hits. One is going to be the main drag equation. The second is going to be a lift equation used for airfoils. And the third is a figure used for sphere cylinders and discs. Now, the word drag does appear in several other sections of the FE exam manual in environmental engineering, but those clearly are not going to fit this problem. But for a regular fluid mechanics section, really just these 3 things: drag, lift, and the figure. For this first question of a moving car, it's pretty straightforward to figure out which one you need based on all the information that you're given. You're asked to find force, you're given area, drag coefficient. These are all the terms in the drag force equation. So let's just plug and chug and see where you get. So the drag force is equal to the drag coefficient, density, area, velocity squared, and there's a 1/2 in there. And of course, density is going to be given to you in slugs because the people who write the FE exam hate you. But that's not actually going to be the tricky part of this problem. Instead, let's look at velocity. We're given 2 velocities for this problem. The car is moving forward at 60 miles per hour and the wind is coming at the car at 20 miles per hour. And which velocity goes in the equation, 60 or 20? Or neither? The actual velocity you need here is 80 miles per hour, right? If the car is driving 60, but the wind is coming at the car with an additional 20, then it feels like the car is going 80, or that the wind hitting the car is going 80. And here's where you see the actual sort of trick of this problem. It's not really a drag problem at all. This problem is really a unit conversions problem. Because you were given miles per hour, but you know miles and hours are not going to cancel with anything, so this has to go to feet per second. So 5,280 feet in a mile and 3,600 seconds in an hour. A little bit of calculator work, 148 slug feet per second squared. But the problem asked for pound force. And luckily, if you just decide at this point to give up on this problem and move on, you actually would get to the correct answer. But if, like me, you always forget what a slug is, just think to yourself, F equals ma. Force equals mass times acceleration. A pound force is equal to a slug times a feet per second squared. And that essentially is the definition of a slug. It's the unit of mass that fits into this equation with pounds force and feet per second squared. And so a 1-to-1 ratio, so the answer actually is 148 pound force. And so the drag force is most nearly D, 150. All right, problem number 2. We got to move fast because your TA Indy is getting anxious. He wants to go running on his wheel, so we got to knock this one out quick. This problem we're hardly given any information, just a Reynolds number and that the shape is a sphere. So you can't use the drag force equation, you're just missing too much information. So remember, the FE exam manual had 3 mentions of drag in the fluid mechanics section: drag force equation, lift equation, and the figure. So since we have almost no information besides Reynolds number, go straight to the figure. And the figure is applicable for spheres, discs, and cylinders. Fortunately, this problem is a sphere. And spheres on this figure are the solid dark line. And the main trick for this problem is just recognizing the axes, right? It's not linear. This is a logarithmic scale axes where each of the major divisions are actually a factor of 10 apart from each other. So don't miss this note down at the bottom of the page. It explains exactly how to read the graph. Intermediate divisions are 2, 4, 6, and 8. So this means that those numbers, say the Reynolds numbers between 1 and 10, it's not 1, 2, 3, 4, right? It's 1, 2, 4, 6, 8, 10. And then 10, 20, 40, 60, 80, 100. So we're given Reynolds number of 20. So that's going to fall right on this line here. Trace that up to the dark spherical line and shift it over there to the left to see where it hits the vertical axis. And again, the same divisions on the vertical axis, 2, 4, 6, and 8, are the division lines on the vertical axis also. This point's between 2 and 4. And remember, of course, 3 would not be right in the middle. The 3 will actually be closer to the 4. So this point might actually be like 2.7. But looking over the answer choices, the answer's clearly going to be E, 2.0 or greater. So celebrate and move on to the next question. If you want to see a longer drag equation problem, something more applicable to a fluid mechanics class like you could see on a homework or test question, then watch this next video you see posted on the screen. It goes a little bit more in depth with free body diagrams and a few other different types of tables and charts where you could look up drag coefficients.